and the core rivalry that builds the foundation for all this logic. Basically, every two-player game in AI features a head-to-head battle between two completely distinct entities, and they have entirely opposite goals. Think of it like a heavyweight boxing match. In one corner, we have the Maximizer. The Maximizer fights for the highest possible score or benefit. It starts out in the deepest hole you can imagine, an initial worst-case value of -infinity, and it desperately wants to climb its way up. In the opposite corner, we've got the Minimizer. Now, the Minimizer wants to completely ruin the Maximizer's day, aiming for the absolute lowest possible score. It starts from a worst-case value of +infinity and tries to drag the score all the way down. They fight it out, with each of them assuming the other's playing flawlessly.
So, how do they actually fight? That brings us to Section 2, the Minimax algorithm, the foundation. This is the baseline algorithm that governs that intense rivalry we just talked about.
By definition, the Minimax algorithm is a recursive or backtracking algorithm used in decision-making. It provides the optimal move for a player, assuming the opponent is also playing optimally, by utilizing a depth-first search. In plain English, that means the algorithm looks as far into the future as possible, going all the way down to the terminal nodes, the very bottom of the game tree, and then it backtracks up using recursion to find the absolute best move. Okay, Section 3. Minimax step-by-step, seeing it in action. You know, definitions are great and all, but seeing this visually is where it really clicks. Let's walk through how this plays out on an actual game tree. In Step 1, we lay out the battlefield. The algorithm generates the entire game tree from the initial state, right at the top, node A, all the way down to the terminal utility values at the bottom. We've got our Maximizer at the top row, the Minimizer in the second row, the Maximizer again in the third, and finally those actual terminal values at the bottom leaves, spanning from -5 all the way up to 7. Moving on to Step 2, we start our backtracking from the bottom. It's the Maximizer's turn at the third layer to start fighting. Starting at node D, the Maximizer compares the terminal values -1 and 4 against its initial -infinity, hunting for the highest number. Obviously, the max is 4, so node D becomes 4. Over at node E, comparing 2 and 6, it takes the 6. For node F, comparing -3 and -5, it takes -3. And for node G, given the choice between 0 and 7, the Maximizer gladly snatches up that massive 7. All right, Step 3. Now the Minimizer takes a turn. Looking to do maximum damage, it compares those values we just found against +infinity, desperately searching for the absolute lowest numbers. At node B, the Minimizer looks at the 4 from D and the 6 from E. The minimum is 4, so B gets dragged down to 4. Over at node C, it compares the -3 from F and the 7 from G. The minimum is -3, so node C pulls up that -3 to really crush the Maximizer's score. Finally, Step 4, we backtrack all the way up to the root node A. The Maximizer takes the final turn, choosing between the 4 at node B and the -3 at node C. Since the Maximizer is always fighting for the highest score, it decisively picks 4. And there we have it. The optimal path is locked in, and the Maximizer secures the win. Which leads us perfectly into Section 4, Properties and Limitations, the fatal flaw. We've just seen how elegant the Minimax algorithm can be, but now we need to talk about its fatal flaw when you actually try to apply it to the real world. First, let's look at the properties. The good news? Minimax is complete, meaning it will absolutely find a solution if one exists. It's also completely optimal, assuming the opponent plays optimally. But take a look at its time and space complexity. They're both O of B to the power of M, where B is the branching factor, the number of choices per turn, and M is the maximum depth. Simply put, the computational workload explodes exponentially with every single turn you take. Let's put that into perspective. In a super simple game like tic-tac-toe, the branching factor is tiny, so checking every node is incredibly fast. But chess? Oh man. Chess is a whole different beast. The branching factor is absolutely huge. There are actually more possible chess games than there are atoms in the observable universe. So, standard Minimax becomes practically useless here because it is just way too slow to compute every single possible move.
So, we're left with this massive problem. How can we cut that exponent in half and make the algorithm fast enough to actually handle complex games?
Enter Section 5, Alpha-Beta Pruning, the ultimate optimization. This is the ultimate hero of our narrative, a solution built specifically to fix Minimax's fatal speed issue. So, alpha-beta pruning is a modified, highly optimized version of the Minimax algorithm. The brilliant part?
It returns the exact same move as standard Minimax, but it computes the correct decision without checking every node by pruning away irrelevant branches. By just snipping off the paths that don't matter, it effectively cuts the exponent in half without sacrificing a single drop of accuracy.
To pull this off, it's like the algorithm develops a memory. It introduces two new threshold parameters. First is alpha. This is the highest value choice or safety net found so far on the maximizer's path. Alpha is only updated by max. Then we have beta. This is the lowest value choice on the minimizer's path. Beta is only updated by min.
And here is the pruning condition, the golden mathematical rule that makes this all work. If, at any point, alpha becomes greater than or equal to beta, we immediately prune the subtree. We just stop traversing that path entirely.
Let's see this in real time. Section 6. How alpha-beta pruning works, step by step. We'll trace these alpha and beta values through a brand new game tree. In step 1, the max player begins at node A with initial values. Alpha starts at -infinity and beta at +infinity. Because we're doing a depth-first search, these exact initial values get passed straight down the left side of the tree, from A to B and all the way down to D. Moving into steps 2 and 3, node D calculates its terminal leaves, which are 2 and 3. Since it's the maximizer's turn, it updates alpha to 3. Then, backtracking to node B, it's the minimizer's turn. Node B looks at that 3 and knows it can force a score of at least as low as 3, so it updates its beta value to 3. So now, at node B, alpha is still -infinity, but beta is 3.
Now step 4. This is where the first prune happens. Node E checks its first leaf, which is 5. Since E is a maximizer, it updates its alpha to 5. But wait a second, look at the parameters. Alpha is 5 and beta is 3. Alpha is now greater than beta. The pruning condition is met. So we immediately prune the right successor node, completely skipping that 9. We just saved valuable computing time right there.
Finally, in steps 5 through 7, we backtrack up to the root node A. Node A updates its alpha to 3, passing alpha 3 and beta infinity down to C, and then to F. Node F evaluates its leaves, takes the max of 1, and passes it up to C. Since C is a minimizer, it updates its beta to 1. Now at node C, alpha is 3 and beta is 1. Once again, alpha is greater than beta. The condition triggers and boom, the entire node G subtree is pruned. We don't even have to glance at the 7 or the 5. It's pretty amazing, right? By eliminating those useless computations, alpha-beta pruning masters complex games in a fraction of the time, while returning the exact same optimal path. So I'll leave you with this thought. If pruning can solve a game tree with more possibilities than atoms in the universe, what other massively complex decision-making systems in our world could this kind of optimization transform? Thanks for joining me on this explainer, and keep exploring.